Hi friends, welcome back to the course on differential calculus. In this session, we discuss functions that are increasing or decreasing. The increasing and decreasing nature of functions will be discussed using first derivatives. We also discuss concavity properties of functions and analyze them using second derivatives. Suppose a person starts to boil water in an open vessel placed over a gas stove. Let T of t denote the temperature of water at time t. The gas stove is turned on at time t equal to 0 and is turned off at time t equal to 16 seconds. Then the temperature T of t of the water goes up in the time range 0 less than or equal to t less than or equal to 16. In other words, temperature T increases as time t progresses from 0 seconds to 16 seconds. We say that temperature of boiling water is an increasing function of time t in the range 0 less than or equal to t less than or equal to 16. However, once the gas stove is turned off at t equal to 16 seconds, the temperature of the water comes down. At this stage, we say that the temperature is decreasing. Function of time t say in the range 16 less than or equal to t less than or equal to 30. The example mentioned just now illustrates that a function may be increasing for some time and decreasing for another time. Intuitively saying, a function y equal to f of x is said to be increasing if the y value increases as the x value increases in some range of x values. More precisely, a function f is increasing on an interval I if for all x and y in the interval I, x less than y implies f of x is less than or equal to f of y. A function f is strictly increasing on I if for all x and y in the interval I, x less than y implies f of x is less than f of y. Similarly, a function y equal to f of x is decreasing if the y value decreases as the x value increases in some range of x values. More precisely, a function f is decreasing on an interval I if for all x and y in the interval I, x less than y implies f of x is greater than or equal to f of y. The function f is strictly decreasing on I if for all x and y in the interval I, x less than y implies f of x is greater than f of y. From the definition, it is clear that any strictly increasing function is increasing and any strictly decreasing function is decreasing. It is important to observe that f is increasing if and only if minus f is decreasing. For example, by looking at the graph, we say that f of x equal to x cube is increasing while minus f of x equal to minus x cube is decreasing. A function which is either increasing or decreasing on an interval I is said to be monotonic on I. Consider the function f of x equal to x square plus 2. For all x comma y in the interval minus infinity to 0, x less than y implies x square is greater than y square. So that f of x equal to x square plus 2 is greater than y square plus 2 equal to f of y. Thus, f is decreasing on minus infinity to 0. On the other hand, for all x comma y in the interval 0 to infinity, x less than y implies x square is less than y square. So that f of x equal to x square plus 2 is less than y square plus 2 equal to f of y. Thus, f is increasing on the interval 0 to infinity. In fact, f of x equal to x square plus 2 is strictly decreasing on minus infinity to 0 and strictly increasing on 0 to infinity. Thus, f is monotonic on minus infinity to 0 and on 0 to infinity separately, but not on the entire real line. Let us examine how monotonicity and differentiability of a function are related. Let f be a differentiable function on an interval a b. If f is increasing on a b, then for any x and y in the open interval a b, we have f of y is greater than or equal to f of x whenever y is greater than x. That is, f of y minus f of x is greater than or equal to 0 for all y minus x greater than 0. That is, f of y minus f of x upon y minus x is greater than or equal to 0. If x comma y is in a b with y less than x, then interchanging the role of x and y, the above inequality becomes f of x minus f of y upon x minus y is greater than or equal to 0. Taking out the minus sign from both denominator and numerator of the LHS and cancelling, we get minus of f of y minus f of x upon minus of y minus x is greater than 0. That is, f of y minus f of x upon y minus x is greater than or equal to 0. Thus, for any x comma y in a b, we have f of y minus f of x upon y minus x is greater than or equal to 0. So, that limit y going to x, f of y minus f of x upon y minus x is greater than or equal to 0. Hence, f dash of x equal to limit y going to x, f of y minus f of x upon y minus x is greater than or equal to 0. In fact, the converse is also true. In fact, from the mean value theorem, which is discussed in the previous session, it follows that if f is differentiable function on a b and x comma y is in a b, then there exists a point c between x and y such that f of y minus f of x equal to f dash of c into y minus x, equation 1. Suppose f dash of x is greater than or equal to 0 for all x in a b. In particular, we have f dash of c is greater than or equal to 0. Thus, if x is strictly less than y, then y minus x is positive. So, we have f of y minus f of x equal to f dash of c into y minus x is greater than or equal to 0. So, that f of y is greater than or equal to f of x. This says that f is increasing on I. Thus, for a differentiable function f on a b, f is increasing if and only if f dash of x is greater than or equal to 0 for all x in the interval a b. Now, suppose f dash of x is greater than 0 for all x in the interval a b. Thus, if x is less than y, then by mean value theorem, we have f of y minus f of x equal to f dash of c into y minus x is greater than 0 for some c between x and y, so that f of y is greater than f of x. This says that f is strictly increasing on the interval a b. The converse of this is not true. In fact, f of x equal to x cube is strictly increasing on the interval minus 1 to plus 1. However, f dash of 0 is equal to 0. Thus, f is strictly increasing on the interval a b does not imply f dash of x is strictly positive for all x in the interval a b. By similar arguments, if f dash of x is less than or equal to 0 for all x in I, then f is decreasing on I, and if f dash of x is strictly less than 0 for all x in I, then f is strictly decreasing on I. All these conclusions are summarized in the following table. If f dash of x is greater than or equal to 0 for all x in I, then f is increasing on I. If f dash of x is strictly greater than 0 for all x in I, then f is strictly increasing on I. If f dash of x is less than or equal to 0 for all x in I, then f is decreasing on I, and if f dash of x less than 0 for all x in I, then f is strictly decreasing on I. Let f be a differentiable function that changes from increasing to decreasing at some point, say x equal to c. Then c is a local maximum, so that f dash of c is equal to 0. Similarly, if f changes from decreasing to increasing at some x equal to c, then c is a local minimum, so that f dash of c is equal to 0. Thus, the derivative of the function, that is f dash of x, takes value 0 when f changes from increasing to decreasing and decreasing to increasing. Let us now analyze the increasing and decreasing nature of f of x equal to x to the power 4 minus 2 x square. Differentiating with respect to x, we obtain f dash of x equal to 4 x cube minus 4 x. Now, f dash of x equal to 0 implies 4 times x cube minus x equal to 0, which gives x minus 1 into x plus 1 equal to 0. Thus, x equal to minus 1, 0 or 1. We note that for no other value of x, f dash of x equal to 0. Thus, it is possible that function f changes its decreasing or increasing nature at minus 1, 0 and 1. Therefore, we analyze the nature of f in each of the intervals minus infinity to minus 1, minus 1 to 0, 0 to 1 and 1 to infinity. Since f dash of x is equal to 4 x cube minus 4 x is continuous and never 0 inside the interval minus infinity to minus 1, f dash of x must be either positive or negative throughout this interval. To see the behavior of f dash of x in this interval, we choose any point, say x equal to minus 2 in the interval minus infinity to minus 1 and obtain that f dash of minus 2 is equal to 4 times minus 2 whole cube minus minus 2, which is equal to minus 24, a negative number. Thus, we have f dash of x is negative throughout the interval minus infinity to minus 1. So, that f of x is strictly decreasing in minus infinity to minus 1. Similarly, taking the point minus half in the open interval minus 1 to 0, we see that f dash of minus half is equal to 4 times minus half to the power 3 minus of minus half, which is equal to 3 by 2, a positive number. So, that f of x is strictly increasing in the interval minus 1 to 0. Now, taking the point half in the open interval 0 to 1, we see that f dash of half is equal to 4 times half to the power 3 minus half, which is equal to minus 3 by 2. So, that f of x is strictly decreasing in 0 to 1. Finally, taking the point 2 in the open interval 1 to infinity, we see that f dash of 2 equal to 4 times 2 cube minus 2 equal to 24, a positive number. So, that f of x is strictly increasing in the interval 1 to infinity. Without taking particular points in each interval, the above conclusions can be drawn from the following table. In the interval minus infinity to minus 1, x minus 1 is negative, x is negative, x plus 1 is negative. Therefore, their product f dash of x equal to x minus 1 into x plus 1 is negative. Therefore, f of x is strictly decreasing. In the interval minus 1 to 0, x minus 1 is negative, x is negative, x plus 1 is positive. So, that their product f dash of x equal to x minus 1 into x plus 1 is positive. So, that f of x is strictly increasing. In the interval 0 to 1, x minus 1 is negative, x is positive, x plus 1 is positive. So, that f dash of x equal to x minus 1 into x plus 1 is negative, and hence f of x is strictly decreasing. And finally, in the interval 1 to infinity, x minus 1 is positive, x is positive, x plus 1 is positive. So, that their product f dash of x equal to x minus 1 into x plus 1 is positive, and hence f of x is strictly increasing. These conclusions can be verified by looking at the graph of the given function. For more clarity, let us consider another function, say f of x equal to 2x minus 3 divided by x square for x not equal to 0. Differentiating the above with respect to x by applying the quotient rule gives f dash of x equal to x square into 2 minus 2x into 2x minus 3 whole divided by x to the power 4 for x not equal to 0, which is equal to minus 2 x square plus 6 x whole divided by x to the power 4, which is equal to minus 2 x into x minus 3 divided by x to the power 4, which is equal to minus 2 into x minus 3 whole divided by x cube for x not equal to 0. Function f is defined only on the interval minus infinity to 0 and 0 to infinity. Further, f dash of x is equal to 0 only at x equal to 3. Thus, the function f changes its decreasing or increasing nature possibly at 0 and 3. Therefore, we analyze the nature of f in each of the intervals minus infinity to 0, 0 to 3 and 3 to infinity. In the interval minus infinity to 0, x minus 3 is negative, x cube is negative, hence f dash of x equal to minus 2 times x minus 3 by x cube is negative, and hence f of x is strictly decreasing. In the interval 0 to 3, x minus 3 is negative, x cube is positive, hence f dash of x equal to minus 2 into x minus 3 by x cube is positive, and hence f of x is strictly increasing. In the interval 3 to infinity, x minus 3 is positive, x cube is positive, and hence f dash of x equal to minus 2 into x minus 3 by x cube is negative, and hence f of x is strictly decreasing. These conclusions can be verified by looking at the graph of the given function. So far, we have analyzed the increasing and decreasing nature of curves using first derivatives. We are now going to discuss the bending nature of a curve. Looking at the graph of the function f of x equal to x cube, we can see that the curve rises as x increases, that is, the function is an increasing one, but the portions of the curve defined on the interval minus infinity to 0 and 0 to infinity turn in different ways. We note that on the open interval minus infinity to 0, the curve has the shape of a cup upside down, so it cannot hold water, while on the interval 0 to infinity, the curve has a shape of a cup, so it can hold water. By looking at the graph, it can be seen that if we take any point x on the interval minus infinity to 0, all the points very near to the point P x comma x cube on the graph lie below the tangent at P. We say that the curve has concave down behavior at the point P. As P x comma x cube is a point corresponding to any x in the open interval minus infinity to 0, we say that the function f is concave down in the open interval minus infinity to 0. On the interval minus infinity to 0, as we move to the right along the x axis up to x equal to 0, tangent lines to the curve have decreasing slopes f dash of x. That is, on the interval minus infinity to 0, the function f dash of x is a decreasing one. By looking at the graph, it can be seen that if we take any point x on the interval 0 to infinity, all points very near the point P x comma x cube on the graph lie above the tangent at P. We say that the curve has concave up behavior at the point P. As P x comma x cube is a point corresponding to any x in the open interval 0 to infinity, we say that the function f is concave up in the open interval 0 to infinity. On the open interval 0 to infinity, as we move to the right along the x axis starting from x equal to 0, tangent lines to the curve has increasing slopes f dash of x. That is, on the interval 0 to infinity, the function f dash of x is an increasing one. We say that the function y equal to f of x is concave up on an open interval if its tangent line have increasing slopes on that interval and is concave down if they have decreasing slopes. In other words, y equal to f of x is concave up on an open interval if its graph lies above its tangent lines on that interval and is concave down if it lies below its tangent lines. We now define concavity in terms of first derivative as follows. If f is differentiable on an open interval, then f is said to be concave up on the open interval if f dash is increasing on that interval, and f is said to be concave down on the open interval if f dash is decreasing on that interval. If the second derivative f double dash x is, then the concavity property of the curve y equal to f of x can be explained in terms of derivatives. In fact, a curve y equal to f of x is concave up in an open interval I if the derivative f dash of x is increasing in I. We know that the function f dash of x is increasing if and only if its derivative f double dash of x is greater than 0. Thus, y equal to f of x is concave up if f double dash of x is strictly positive. Similar result holds for concave down property. These ideas are contained in the following test for concavity. The second derivative test for concavity. Let y equal to f of x be twice differentiable on an interval I. 1. If f double dash is strictly positive on the interval I, then the graph of f over I is concave up. 2. If f double dash is strictly negative on the interval I, then the graph of f over I is concave down. As an example, we have already observed that the curve y equal to x cube is concave down on minus infinity to 0 and concave up on 0 to infinity. This is justified by the second derivative test also, because on the open interval minus infinity to 0 we have y double dash equal to 6x which is less than 0, and on the open interval 0 to infinity we have y double dash equal to 6x which is greater than 0. As another example, referring the graph of the parabola f of x equal to x square and taking a point A on it, we see that all points near A lies above the tangent at A. Similar situation arises at the point B. Similarly, at any point P on the graph of the parabola y equal to x square, all points near P lies above the tangent at P. This shows that the parabola y equal to x square is concave up at any point P on the parabola y equal to x square. We say that f of x equal to x square is concave up throughout the entire real line. This is justified by the second derivative test also, because f double dash of x equal to 2 is greater than 0 for any real value of x. Now, we consider the function g of x equal to minus x square. It can be seen that g of x equal to minus f of x, where f of x equal to x square. So, we expect the concave down behavior for g of x equal to minus x square. This is so as by the second derivative test g double dash of x equal to minus 2 is strictly less than 0 for any real value of x. This also can be seen by observing the graph of g of x equal to minus x square. As another example, we analyze the concavity property for the function f of x equal to x cube plus 2x plus 1 using the second derivative test. Differentiating with respect to x, we have f dash of x equal to 3x square plus 2, and differentiating once again we obtain f double dash of x equal to 6x. From this, we see that x less than 0 implies f double dash of x is less than 0, and x greater than 0 implies f double dash of x is greater than 0. Thus, the curve is concave down in the interval minus infinity to 0 and concave up in the interval 0 to infinity. In this example, the curve is concave down to the left of x equal to 0 and concave up to the right of x equal to 0. Thus, the curve changes its concavity property at x equal to 0. Such a point is called point of inflection. If f is continuous on an open interval containing a value x naught, and if f changes the direction of its concavity at the point x naught comma f of x naught, then we say that f has an inflection point at x naught, and we call the point x naught comma f of x naught on the graph of f an inflection point of f. The tangent at the inflection point is called an inflectional tangent. As an example, the function f of x equal to x cube plus 2x plus 1 has an inflection point at x naught equal to 0, and the point 0 1 on the graph is an inflection point of f. The inflectional tangent to the function at the point 0 1 is obtained as follows: f dash of x equal to 3x square plus 2 evaluated at x equal to 0 is 2. Hence, slope of the tangent is 2, and the equation of the tangent at the point 0 1 is given by the point slope form y minus 1 equal to 2 into x minus 0. That is, y equal to 2x plus 1 is the inflectional tangent to the function at the point 0 comma 1. As another example, consider f of x equal to x divided by 1 plus x square. Then, by applying the quotient rule of differentiation, we obtain f dash of x equal to 1 plus x square into 1 minus 2x into x divided by 1 plus x square whole square, which is equal to 1 minus x square divided by 1 plus x square whole square, and f double dash of x equal to 1 plus x square whole square into minus 2x minus 1 minus x square into 2 times 1 plus x square into 2x whole divided by 1 plus x square whole to the power 4, which is equal to 2x into minus 1 minus x square minus 2 plus 2x square whole divided by 1 plus x square whole to the power 3, which is equal to 2x into x square minus 3 divided by 1 plus x square whole cube, and which is equal to 2 into x minus 3 into x plus 3 divided by 1 plus x square whole cube. The denominator 1 plus x square whole cube is always positive. F double dash of x equal to 0 only at the 3 points minus 3, 0 and plus 3. Hence, we analyze the concavity property of the function in each of the intervals minus infinity to minus 3, minus 3 to 0, 0 to 3 and 3 to infinity. We have f double dash of x is continuous in each of these intervals and does not vanish. Hence, the given function is either concave up or concave down in each of these intervals. F double dash of minus 4 is equal to minus 56 divided by 4913. Hence, f is concave down in the interval minus infinity to minus 3. F double dash of minus 1 is equal to 2. Hence, f is concave up in the interval minus 3 to 0. F double dash of 1 is equal to minus 2. Hence, f is concave down in the interval 0 to 3, and f double dash of 4 is equal to 56 divided by 4913. Hence, f is concave up in the interval 3 to infinity. Above conclusions can also be verified from following table. In the interval minus infinity to minus 3, x minus 3 is negative, x is negative, x plus 3 is negative. Hence, f double dash of x equal to 2x into x minus 3 into x plus 3 whole divided by 1 plus x square whole to the power 3 is negative. Thus, f of x is concave down. In the interval minus 3 to 0, x minus 3 is negative, x is negative and x plus 3 is positive. Hence, f double dash of x equal to 2x into x minus 3 into x plus 3 whole divided by 1 plus x square whole to the power 3 is positive. Thus, f of x is concave up. In the interval 0 to 3, x minus 3 is negative, x is positive, x plus 3 is positive. Hence, f double dash of x equal to 2x into x minus 3 into x plus 3 whole divided by 1 plus x square whole to the power 3 is negative. Thus, f of x is concave down. And finally, in the interval 3 to infinity, x minus 3 is positive, x is positive, x plus 3 is positive. Hence, f double dash of x equal to 2x into x minus 3 into x plus 3 whole divided by 1 plus x square whole to the power 3 is positive, and hence f of x is concave up. Thus, we have inflection points at x equal to minus 3, 0 and 3. These conclusions can be verified by looking at the graph of the given function. Further, two things can be observed about inflection points. Firstly, a point need not be an inflection point even if the second derivative vanishes. In other words, f double dash of x naught equal to 0 does not say that x naught comma f of x naught is an inflection point. It says that x naught comma f of x naught is possibly an inflection point. For example, consider the function f of x equal to x to the power 4, then f dash of x equal to 4x cube and f double dash of x is equal to 4x square. Hence, f double dash of x is greater than 0 for all x not equal to 0, so that the curve is concave up to the left and to the right of x equal to 0. Hence, 0 comma 0 is not an inflection point. However, f double dash vanishes at x equal to 0. The second observation is that the derivatives need not exist at an inflection point. For example, f of x equal to x to the power 1 by 3 is not differentiable at x equal to 0. However, the second derivative f double dash of x equal to minus 2 by 9 x to the power minus 5 by 3 x is for x not equal to 0, which is positive for x less than 0 and negative for x greater than 0. Hence, the curve is concave up to the left of x equal to 0 and concave down to the right of x equal to 0. Hence, 0 comma 0 is an inflection point and y axis is an inflectional tangent. As a final example, we consider the function f of x equal to sin pi x. Here f dash of x equal to pi cos pi x and f double dash of x equal to minus pi square sin pi x. We note that since sin theta is 2 pi periodic, we have sin pi into x plus 2 is equal to sin pi x plus 2 pi equal to sin pi x. Thus, the function sin pi x is 2 periodic. By looking at the graph of sin pi x, we can see that for any integer n, sin pi x is greater than 0 in the interval 2n to 2n plus 1 and sin pi x is negative in the interval 2n plus 1 to 2n plus 2. From this, it follows that f double dash of x equal to minus pi square sin pi x is less than 0 in the interval 2n to 2n plus 1 and f double dash of x equal to minus pi square sin pi x is greater than 0 in the interval 2n plus 1 to 2n plus 2. Thus, for any integer n, the curve is concave down in 2n to 2n plus 1 and concave up in the interval 2n plus 1 to 2n plus 2. Thus, n comma 0 is an inflection point for each integer n. This example shows it is possible that a function may have infinitely many inflection points. Conclusion: in this session, we have analyzed monotonicity properties of functions using first derivatives and concavity properties using second derivatives. In fact, the first derivative helps us to identify the rise and fall of functions, and second derivatives to determine the bending nature. Hope you all get benefit